A very good morning to all of you who have joined for this session. I am Rahna Bivi, Project Officer, Energy Efficient Building Cell, EMC Kerala. As we all know, we have been witnessing climate change in real through various incidents around the globe. Energy efficiency is one of the key tools to combat and mitigate climate change and ensure the sustainability of life on the planet. ECBC is one of the flagship programs of Bureau of Energy Efficiency to improve energy efficiency in commercial and residential sector and decarbonize the built environment. Through this two-day program, the EEB cell EMC aim to spread awareness about ECBC and train professionals on daylighting simulation. I invite Mr. Dinesh Kumar, who is the Head of Energy Conservation in Buildings, Outreach Programs, Standards and Labeling, and Small Hydel Development at Energy Management Center, Kerala, for the welcome speech.
A very good morning to all. Let me, on behalf of Energy Management Center, welcome all the learned speakers and respected participants to this training program. I believe I may not have to describe much on what EMC is and our activities, but for the information of those who are new to this session, EMC or Energy Management Center is an autonomous center under the Department of Power, Government of Kerala, and the EMC is engaged in capacity building, advocacy campaigns, awareness creation, research studies, etc. in energy conservation, in addition to our statutory responsibilities entrusted as the state designated agency of Government of India, Bureau of Energy Efficiency. As part of our statutory powers, EMC take care of the activities related to energy conservation, building code implementation, standards and labeling, PAT and designated consumers program, certified energy auditors and managers program, demand state management activities in agriculture and municipal sector, and also on inspection and ensuring proper penetration of the star label products. Friends, you may agree that Kerala, due to its unique characters in energy conservation and energy consumption, has about 50% of its electrical energy being utilized in the domestic sector, and more than 15% goes to the commercial sector, which includes all hospitality, offices, institutions, healthcare, and all other buildings. Thus, about 2/3 of this electricity goes to the building sector, which is a fast booming sector of the economy of the state. There are a lot of buildings coming up in hospitality and tourism sector and IT and healthcare sector. And as everyone knows, the climate change effects are creating a situation where we need to address energy utilization in a changed perspective with a view to conserve energy and use it optimally. This training program, as mentioned, the Energy Conservation Building Code training program, awareness creation, is meant to give such initial awareness on ECBC and recent developments on the Energy Conservation Building Code as prepared by the Bureau of Energy Efficiency, Government of India. The energy till now, the Energy Conservation Building Cell was operational in Energy Management Center. This year onwards, the cell has been renamed as Energy Efficient Building Cell. And EEB cell intends to provide technical assistance to implement and enforce Energy Conservation Building Code and Eco-Nivas Samhita in Kerala state. The EEB cell also provides assistance to commercial and residential buildings to ensure ECBC and ENS or Energy Eco-Nivas Samhita compliant design. It also plans to organize this year. It also plans to organize ECBC and ENS related awareness and training program a total of 19 numbers through online or physical mode. The ECBC is also planning to have a star rating and commercial and star rating program on commercial and residential buildings as part of this Bureau of Energy Efficiency scheme. Now, coming back to today's session. We are going to is on awareness creation on ECBC code as such, and my job is to invite the learned speakers to the session. First of all, our director, Dr. R. Kumar, he will be giving the keynote address for this program. I welcome him to this program. And Mr. Akshay Gupta, he is a renowned master trainer of ECBC. He is giving us this lecture for this session. I welcome him also to this program. Last but not least, I welcome all the participants and the coordinators of this program. With this, I hand over the mic to our director, Dr. R. Kumar, to give a keynote address. Welcome, sir. Thank you.
Namaskaram. Kekkalale. Namaskaram. Kekkalale. ഈ പരിപാടിയിൽ പങ്കെടുക്കുന്ന എല്ലാവർക്കും EMCയുടെ ഭാഗത്തു നിന്ന് ഒന്നുകൂടി സ്വാഗതം പറയുന്നു. കുറച്ച് നാൾക്ക് ശേഷമാണ് ECBC എനർജി എഫിഷ്യൻസി ബിൽഡിങ്ങിനെ സംബന്ധിച്ചുള്ള ഒരു അവയർനെസ് പ്രോഗ്രാം എന്നുള്ള നിലയിൽ EMC നടത്തുന്നത്. 2007 ഇത് വരികയും 2017 കേരളത്തിൽ നോട്ടിഫൈ ചെയ്യുകയൊക്കെ ചെയ്ത ആ സമയത്ത് ഒട്ടേറെ പരിപാടികൾ EMC ഒരു അവയർനെസ് പ്രോഗ്രാം എന്നുള്ള നിലയിൽ നടത്തി. ഏതാണ്ട് ഒരു 2200ഓളം എഞ്ചിനീയേഴ്സിനെ 1 day 2 day അവയർനെസ് പ്രോഗ്രാം എന്നുള്ള നിലയിൽ ഒരു ട്രെയിനിങ് കൊടുത്തിട്ടുണ്ടായിരുന്നു. ഇപ്പോ നിങ്ങൾക്ക് അറിയാവുന്നത് പോലെ നമ്മളെ മുനിസിപ്പൽ ബിൽഡിംഗ് റൂൾസിലും പഞ്ചായത്ത് ബിൽഡിംഗ് റൂൾസിലും നോട്ടിഫൈ ചെയ്തു കഴിഞ്ഞു. ആ സാഹചര്യത്തിൽ പിന്നെ അതൊരു നിയമപരമായിട്ട് നമ്മൾ നിർബന്ധമായിട്ടും 100 കിലോവാട്ടിന് മുകളിൽ ലോഡുള്ള ബിൽഡിങ്ങും 500 സ്ക്വയർ മീറ്ററിന് മുകളിൽ എയർ കണ്ടീഷൻഡ് ഏരിയ ഉള്ള ബിൽഡിംഗ് ഇത് നിർബന്ധമായിട്ടും ചെയ്യണമെന്നുണ്ട്. പക്ഷേ ഈ ഞങ്ങളുടെ ഇടയ്ക്ക് ഒരു കഴിഞ്ഞ കുറച്ച് മാസങ്ങൾക്ക് മുമ്പുള്ള ഒരു റിവ്യൂവിലാണ് ഞങ്ങൾ തന്നെ തിരിച്ചറിഞ്ഞത്, ഒരു ബിൽഡിംഗ് പെർമിറ്റിന് വേണ്ടി പഞ്ചായത്തിൽ അപ്ലൈ ചെയ്യുമ്പോൾ ആ ബിൽഡിംഗ് പെർമിറ്റിന്റെ ആപ്ലിക്കേഷൻ ഫോമിലോ അല്ലെങ്കിൽ അതിന്റെ ഡ്രോയിങ്സിലോ ഒന്നും തന്നെ എത്ര ലോഡാണ്, കണക്റ്റഡ് ലോഡ് എത്ര ഉണ്ട് എന്നത് ഒരു ആപ്ലിക്കന്റിനെ സംബന്ധിച്ചിടത്തോളം അല്ലെങ്കിൽ ഒരു ലൈസൻസ്ഡ് എഞ്ചിനീയറിനെ സംബന്ധിച്ചിടത്തോളം ബിൽഡറിനെ സംബന്ധിച്ചിടത്തോളം മെൻഷൻ ചെയ്യേണ്ട ആവശ്യം ഇല്ല എന്ന് കണ്ടത്. അപ്പോൾ മെൻഷൻ ചെയ്യേണ്ട ആവശ്യമില്ല എന്നുണ്ടെങ്കിൽ സ്വാഭാവികമായിട്ടും പഞ്ചായത്തിൽ ഇരിക്കുന്ന എഞ്ചിനീയേഴ്സ് കുറേയേറെ പേര് ഒരുപക്ഷെ ഈ പ്രോഗ്രാമിൽ ചിലപ്പം പങ്കെടുക്കുന്നുണ്ടാകും. നമുക്കിപ്പോൾ എല്ലാം കൂടെ 62 പേര് ഈ പ്രോഗ്രാമിൽ പങ്കെടുക്കുന്നുണ്ട്. അപ്പൊ അവരെ സംബന്ധിച്ചിടത്തോളം ഈ സാധനം കൈ കിട്ടിക്കഴിഞ്ഞാൽ അതിനകത്ത് 100 കിലോവാട്ടിന് മുകളിലുണ്ട് എന്ന് എഴുതി വെച്ചിട്ടുണ്ടെങ്കിൽ മാത്രമേ അതിനകത്ത് ECBC കംപ്ലൈന്റ് ചെക്ക് ചെയ്യേണ്ട ആവശ്യം വരുന്നുള്ളൂ. സോ അതിനകത്ത് പറയാത്തിടത്തോളം കാലം ദേ ആർ ഓൾസോ ഹെൽപ്ലെസ്. അവർക്ക് ഇത് പിന്നെ ECBC കംപ്ലൈന്റ് ആണോ വേണ്ടയോ എന്ന് നോക്കേണ്ട ഒരു ആവശ്യം ഇല്ലാത്തൊരു സാഹചര്യം ഉണ്ടായിരുന്നു. അത് പിന്നെ ഇപ്പോൾ ഒരു മാറ്റം വന്നിട്ടുണ്ട്. ഈ അടുത്ത കാലത്ത് ഇലക്ഷന് ശേഷം നമുക്ക് ഞാൻ പറഞ്ഞു വന്നത് പിന്നെ പുതിയ അമെന്റ്മെന്റില് ഇലക്ഷന് ശേഷം വന്ന പുതിയ അമെന്റ്മെന്റിൽ കിലോ വാട്ട് ഡിക്ലെയർ ചെയ്യണം എന്ന് പറഞ്ഞിട്ടുള്ള അമെന്റ്മെന്റ് വന്നിട്ടുണ്ട്. അതിന്റെ അടിസ്ഥാനത്തിൽ അത് ലൈസൻസ്ഡ് എഞ്ചിനീയർ ആയാലും ബിൽഡർ ആയാലും അപ്ലൈ ചെയ്യുമ്പോഴത്തേക്ക് വി ഹാവ് ടു ഡിക്ലെയർ. അത് ഡിക്ലെയർ ചെയ്തിട്ടുണ്ടോ എന്ന് നോക്കാനുള്ള ഉത്തരവാദിത്വം LSD എഞ്ചിനീയേഴ്സിനുണ്ട്. 100 കിലോ വാട്ടിന് മുകളിലാണെന്നുണ്ടെങ്കിൽ അത് അവര് ECBC കംപ്ലൈന്റ് ചെക്ക് ചെയ്യാനുള്ള ഉത്തരവാദിത്വം ഉണ്ട്. അവർക്ക് അവിടെ ചെക്ക് ചെയ്യാൻ പറ്റുന്നില്ല എന്നുണ്ടെങ്കിൽ ഇതൊരു സിമുലേഷൻ എക്സസൈസ് ചെയ്യാനായിട്ടുള്ള സമയക്കുറവോ കോമ്പീറ്റൻസ് കുറവോ അവർക്ക് ചെയ്യാൻ പറ്റുന്നില്ല എന്നുണ്ടെങ്കിൽ ഡെഫിനറ്റ്ലി യു ക്യാൻ സെൻഡ് ഇറ്റ് ടു അവർ ECBC സെൽ ഫംഗ്ഷനിങ് വിത്തിൻ EMC. നമ്മൾ അത് ചെക്ക് ചെയ്ത് തരുന്നതായിരിക്കും. അത് നിങ്ങൾക്ക് ആ ലൈസൻസ്ഡ് എഞ്ചിനീയേഴ്സിന്റെ അടുത്തോ ബിൽഡേഴ്സിന്റെ അടുത്തോ തന്നെ ആവശ്യപ്പെടാം. EMCയുടെ കംപ്ലയൻസ് ചെക്കോട് കൂടി വരാനായിട്ട് പറയാം. അപ്പൊ ഇത് ആണ് നേരത്തെ സെല്ലിന്റെ ഒരു പ്രവർത്തനം ഒതുങ്ങി നിന്നത്. പക്ഷെ ഞാൻ അതും പറഞ്ഞിട്ടുണ്ടായിരുന്നു, കേട്ടില്ല എന്ന് തോന്നുന്നു. പിന്നെ ഇത് വെൻ ദ ലോഡ് ഇൻക്രീസസ്, നമ്പർ ഓഫ് ആപ്ലിക്കേഷൻസ് വരുന്നത് ഇൻക്രീസ് ചെയ്യുകയാണെങ്കിൽ, ഇന്നലെ വരെ അത് ആപ്ലിക്കേഷൻസ് വരാതിരുന്നത് ഈ 100 കിലോ വാട്ടിന്റെ ഡിക്ലറേഷൻ ഇല്ലാത്തത് കൊണ്ടാണ്. In number of applicants increase, we will not be able to cater to the load, and therefore we have created a new cadre called Building Energy Efficiency Experts, BEEE എന്ന് പറഞ്ഞിട്ട്. അതിനകത്ത് ഉള്ള ആൾക്കാർ ഇതിനകത്ത് ചിലപ്പം കേൾക്കാനായിട്ടിരിക്കുന്നുണ്ടോ എന്ന് ഒന്നോ രണ്ടോ പേരെ ഞാൻ പേര് ഓർമ്മയുള്ളവരെ ഞാൻ കണ്ടതായിട്ട് ഓർക്കുന്നു. അപ്പോൾ ഏതായാലും അങ്ങനെ ഒരു കാഡറിനെ നമ്മൾ ഡെവലപ്പ് ചെയ്തിട്ടുണ്ട്. സോ യു ക്യാൻ അവെയിൽ ദെയർ സർവീസസ്. ഈ LSG എഞ്ചിനീയേഴ്സിനും അവരുടെ കംപ്ലയൻസ് ചെക്കിന് വേണ്ടി അവരുടെ സർവീസസ് ലേക്ക് പോകാം. അത് നേരിട്ട് വേണമെങ്കിലും പോകാം, അല്ലെങ്കിൽ ത്രൂ EMCയുടെ സെല്ല് വഴി അയച്ചു തന്നു കഴിഞ്ഞാൽ ഞങ്ങൾ അവരുടെ സർവീസ് എടുത്തിട്ട് അവരെ കൊണ്ട് ഇവാലുവേറ്റ് ചെയ്തിട്ട് വി വിൽ ഗീവ് ദ റിപ്പോർട്ട് ബാക്ക് ടു ദ LSG. ആ രീതിയിൽ വേണമെങ്കിലും ചെയ്യാം. തിരിച്ച് പിന്നെ ഈ ഒരു ബിൽഡറിനെ സംബന്ധിച്ചിടത്തോളം ബിഫോർ ഹി സബ്മിറ്റ് ദ പ്ലാൻ ടു ദി LSG, ഹി ക്യാൻ ഹാവ് എ ECBC കംപ്ലയൻസ് ചെക്ക് ചെയ്തതിന് ശേഷം, ഈ BEEE സർട്ടിഫൈഡ് ആൾക്കാരെ കൊണ്ട് കംപ്ലയൻസ് ചെക്ക് ചെയ്തതിന് ശേഷം പിന്നെ നിങ്ങൾക്ക് പിന്നെ ഇതിലേക്ക് സബ്മിറ്റ് ചെയ്യാനായിട്ടുള്ള സാഹചര്യവും ഉണ്ട്. അപ്പോൾ ഇതിന്റെ BEEE EMC മാത്രം ഈ ട്രെയിനിങ് പ്രോഗ്രാം നടത്തി ഇങ്ങനെ ഒരു കാഡറിനെ കൊണ്ടുവന്നു കഴിഞ്ഞാൽ ആയിരക്കണക്കിന് ആളുകളെ കൊണ്ടുവരാൻ പറ്റൂല എന്നുള്ള തിരിച്ചറിവിന്റെ ഭാഗമായിട്ട് വി ഹാവ് started collaborating with different institutions, private consultancy organizations ആയാലും ECBC master trainers organizations, otherwise professional associations, Lenswed പോലെയുള്ള ഇൻസ്റ്റിറ്റ്യൂഷൻ ഓഫ് എഞ്ചിനീയേഴ്സ് പോലെയുള്ള പ്രൊഫഷണൽ അസോസിയേഷൻ, കൊല്ലത്തുള്ള ഇന്റർനാഷണൽ ഇൻസ്റ്റിറ്റ്യൂട്ട് ഫോർ കൺസ്ട്രക്ഷൻ മാനേജ്മെന്റ് എന്ന് പറയുന്ന ആ സ്ഥാപനം, എഞ്ചിനീയറിംഗ് കോളേജസ്, ഇങ്ങനെയുള്ളവരുമായിട്ടൊക്കെ ഞങ്ങൾ പിന്നെ ഈ പ്രോഗ്രാം പിന്നെ റൺ ചെയ്യാനായിട്ടുള്ള ചർച്ചകളിലാണ്. പിന്നെ അതിനെക്കുറിച്ചുള്ള അതിന്റെ ഈ അടുത്ത കാലത്ത് പ്ലാൻ ചെയ്തിട്ടുള്ള ട്രെയിനിങ് പ്രോഗ്രാം എന്തെങ്കിലും ഉണ്ടെങ്കിൽ അതിനെക്കുറിച്ചുള്ള ഡീറ്റെയിൽസും പിന്നെ ഈ പ്രോഗ്രാമിന്റെ ഇടയിൽ ഞങ്ങളുടെ ECBC സെല്ലിലുള്ള ഉദ്യോഗസ്ഥരെ പറയുമെന്നാണ് ഞാൻ പ്രതീക്ഷിക്കുന്നത്. ഇത്രയും പറഞ്ഞുകൊണ്ട് ഈ വന്നിരിക്കുന്ന എല്ലാവരും ഒന്നുകൂടെ സ്വാഗതം ചെയ്തുകൊണ്ട് നിർത്തുന്നു. നന്ദി, നമസ്കാരം. താങ്ക് യു വെരി മച്ച്.
Thank you, sir. So today we have our ECBC. Thank you, sir. So today we have our ECBC Master Trainer, Mr. Akshay Kumar Gupta with us. He is currently working as the Director of Passive Design Consultants, Noida. He has about 13 years of experience as a green building consultant in the UK and India. He has been involved in conducting many professional training workshops across India. The training programs include ECBC training and capacity building programs and Griha training programs for professionals and students. He is also a visiting faculty of School of Planning and Architecture, New Delhi. We are extremely thankful to you, sir, for your presence here. I welcome Mr. Akshay Kumar Gupta for the session. Over to you, sir.
Hi, thank you, ma'am. Thank you so much for the introduction. And very good morning to all the participants and the organizers. I hope my screen is visible now. Please confirm.
Sir, yes, sir, your screen is visible.
So, thank you again for inviting me for this awareness program on Kerala State Energy Conservation Building Code. And thank you EMC for organizing this and creating awareness in the state for energy conservation in buildings. Like for today's agenda, for my part is basically to share and create awareness on ECBC. I'll just skip this slide as you have already introduced me. Kerala State ECBC. So I'll start with the very basic of what is ECBC. See, ECBC is a code. It's Energy Conservation Building Code. It's a code, as the name itself suggests. It's a code for buildings for energy conservation. ECBC originally was introduced in 2007 by Bureau of Energy Efficiency. And Bureau of Energy Efficiency in 2001, they came up with Energy Conservation Act, under which they felt that there is a dire need of making our buildings energy efficient, and not just buildings, but making our country energy efficient. So Bureau of Energy Efficiency brought this act, Energy Conservation Act in 2001, and they started working on multiple areas for energy conservation. So they came up with a star labeling program where the electric. So I was talking about Bureau of Energy Efficiency in 2001. They came up with Energy Conservation and Building Act. And under this act, they took several measures and initiatives to bring awareness on energy efficiency in the country. They came up with a star labeling program where they started labeling different home appliances like air conditioners, ceiling fans, refrigerators, televisions, the major energy consuming home appliances and equipments, even lighting systems. And the initiative basically talked about or addressed creating awareness for the end consumers, where we as end consumers can choose a product based on its energy efficiency. So different appliances would be rated from 1 star to 5 star, 5 star being the most efficient ones. So that when we are buying new equipments, we purposefully and admittedly select systems which are more efficient. Even if we are paying little extra for it, we know why we are paying little extra for it. On the same lines, they realize that the buildings need to be energy efficient as well. The buildings consume more than 40% of the global annual energy consumption or carbon emissions. So, which means that buildings contribute to 40% carbon emissions and 40%, approx 40% of the total energy consumption worldwide. And these buildings are commercial buildings, homes, industries, etc. Hence, it is very important that we make our buildings energy efficient. So for that, they came up with Energy Conservation Building Code in 2007. That was the first time when Energy Conservation Building Code was launched. And this code talked about different guidelines, several measures that needs to be adopted in a building in order to make sure that the building is energy efficient, in order to make sure that the building conserves energy as compared to a conventional building. And moving forward, many states in the country adopted it, Kerala being one of the states who adopted Energy Conservation Building Code. Initially, it was not a mandatory requirement. The states adopted it and mandated it in their own project, in their own states, so that all the buildings which are applicable as per ECBC will have to show compliance to this code in order to make sure that all new buildings are energy efficient. Now, in 2017, like I said, the second version or the latest version of ECBC was launched. Kerala state also adopted it and renamed it as Kerala State ECBC or Kerala State Energy Conservation Building Code 2017. This particular code is basically the only difference between the general ECBC 2017 and Kerala State ECBC 2017 is that Kerala State ECBC 2017 code only talks about the requirements of Kerala. The general ECBC talks about all different kind of climates, all different state requirements, because we have a vast country moving from north to south or east to west. We have 5 different climates. We have 5 different climates, and under these 5 different climates, the requirement for buildings also change. The building physics also change. So the buildings have to be designed in a slightly different manner for all different climates. Hence, as the Kerala state has adopted and notified its own ECBC, they simply considered the requirements which are applicable for the state of Kerala. For this, the ECBC is applicable for certain kind of buildings. These kind of buildings include commercial buildings, retail, shopping complexes and malls, hotels, hospitals, group housing complexes, and even institutional projects. All these projects need to meet the requirement of Energy Conservation Building Code, except for industrial buildings. The buildings under these categories, and if they have a total connected load of more than 100 kilowatt or total contracted electrical load of 120 kVA, or the project has more than 500 square meter of air conditioned area, then these buildings would be needing to meet ECBC. Now, both new buildings which fall under these criteria and meet these criteria have to meet it, as well as the buildings which are retrofit. The buildings which meets these criteria and are doing any renovation, any retrofit, any change in air conditioning system or exterior wall assemblies or glass or any kind of system in the building which are going under any retrofit or renovation will need to meet that particular requirement of ECBC. As I said, industrial buildings and industrial buildings are exempted from this code. Why are the industrial buildings exempted? Industrial buildings have the major component of electrical load or energy load of the plants. So industrial buildings are majorly meant for the plant loads or plant working. Hence, industrial buildings were exempted from the code, and so they are exempted basically. The second category of buildings which are exempted for showing compliance to ECBC are buildings which do not consume any electricity or any other fossil fuel. Fossil fuel means any petroleum-based product like petrol, diesel, kerosene, even natural gas, compressed natural gas, LPG, NPG, etc. Coal, for that matter as well. So if a building is completely off the grid and is not consuming any kind of fossil fuel, then that particular building can also be exempted from ECBC. These buildings can be working on renewable energy. So they might be working 100% on the renewable source of energy, like solar panels, like wind energy, like geothermal energy, like hydropower. Not hydropower, hydropower is not that, but any renewable energy, if they are based out of, they're working on, then and if it is completely meeting its 100% energy requirement through non-fossil fuel based fuel, then that particular building will also be exempted from Energy Conservation Building Code. The reason is very simple. Energy Conservation Building Code is designed and meant to reduce electricity consumption, is meant to reduce the building's carbon emission and extra load on the grid supply and fossil fuels, which are a limited resource on Earth. So any building which is not using these electricity or fossil fuel based fuels, then they are exempted to show compliance. What do we need to submit? So there are certain documentation requirements for showing compliance to ECBC. As a project team, for every project, typically project team needs to get approvals on the drawings, plan sections, elevations, overall project DBR. Similarly, for ECBC compliance, the same approval set has to be submitted for documentation for ECBC. ECBC has requirements regarding air conditioning systems, electrical systems, and many other building materials and equipments. All these materials and equipments which are related to show compliance to ECBC, the project team has to submit their technical specification sheets, purchase invoices, and details, 100% details regarding all those items and materials in the project.
GHGM amendment.
Along with that, there are several compliance calculations for ECBC, which has to be submitted, and ECBC compliance. All these as a complete set has to be submitted before the project is also, when the project is completed, At that particular stage, the project team again has to submit, because in the initial stage, when the building has not, the construction has not started, a lot of details like purchase invoices will not be available with the project team, as the material has yet not been procured at site. However, whether the project team has really fulfilled its commitment of installing the same equipments and materials, to show that compliance, the project team has to submit the invoices, etc., as well as a part of final documentation. Service hot water, pumping, lighting, and electrical power. Now, why do we have these 5 sections? These 5 sections are important because building envelope, which means the outer skin of the building, which means the surfaces of the building which divide outside from the inside, are qualified or are classified as building envelope. These include your roof, exterior walls, exterior windows, doors, etc. These components, because they have to deal with the outdoor environment, they should be designed in a state like Kerala. They should be designed such that we do not allow the heat from outside to come in, especially if the building is air conditioned. At the same time, we want ventilation to be available. So how should the envelope be designed? We also want daylight should come in from outside to inside, but we do not want the solar heat to come inside the building to optimize our air conditioning loads. So the requirements related to the walls, roof, windows, kind of glass we choose, kind of waterproofing, not waterproofing, the air tightness membranes or air tightness that we design for the building, the doors, windows, etc., have to meet the requirement of building envelope section of Kerala State ECBC. Secondly, heating, ventilation, and air conditioning section. This particular section talks about the air conditioning systems or the thermal comfort systems in the building. Many buildings in Kerala are not air conditioned but are naturally ventilated. So this section also talks about the requirements of natural ventilation. If the building is meeting its ventilation requirement through natural ventilation, then what it should do. If the building is not intended for natural ventilation but is designed to be an air conditioned building, then how should mechanical ventilation be done? How should the air conditioning system be installed? What should be the efficiencies of air conditioning systems, chillers, pumps, cooling towers, duct insulation, ducting, chilled water piping, refrigerant piping, etc. in the building? All these requirements and their compliances are given in heating, ventilation, and air conditioning section. The service hot water and pumping section includes how the hot water requirement can be met in a building if it has hot water requirement, and the pumps. Further, moving on to the lighting section, it deals with the lighting requirement. As we all know, the lighting can be of 2 types. It can be natural lighting through daylight, or it can be artificial lighting. So this lighting section talks about both how to integrate daylight in your building design so that your dependency on artificial lighting is minimized. What kind of automatic controls should the building install? What kind of artificial lighting controls should the building install in order to ensure conservation of energy? What should be the allowed efficiency of the artificial lighting that you install in the building? Those are the kind of systems that and the requirements that this section talks about. Lastly, the electrical power section deals with how different electrical equipments in the building are installed and designed or recommended to be installed in the project. This includes transformers, as they are the first line of equipment which integrates the city or municipal grid network to your building's energy network. So how the transformers are, what is the kind of transformer you're using in the project, what is the efficiency level of the transformers. And then from there on, within the project, how is the energy, electrical power distributed cable sizing, losses in the power cables, the electrical motors that we use in project for different purpose, like air conditioning systems or like domestic water pumping, like STP water pumping, etc. Different kind of motors that we installed in the project. What should be the minimum efficiencies of these equipments? Requirement related to renewable, what should be the scope or minimum integration of renewable energy in the building? And lastly, the requirements related to meter. How should we install energy meters in our building for proper monitoring? So how can we monitor our building energy consumption? How can we monitor the different energy consumption areas so that in future, if there is any discrepancy in energy consumption, if there is any usual electricity load or bill, we can pinpoint exactly why there is an anomaly, why any particular area is consuming more energy. So that can be pinpointed by proper metering and monitoring. So you can now understand why we have these 5 major sections in the Kerala State Energy Conservation Building Code and what are the in these sections. Energy Conservation Building Code 2017 and the previous one, Energy Conservation Building Code 2007, they both addressed the issue of different climates in India. India primarily has 5 different climates, as we all know. In the north, especially where we have hills and mountains, the climate is predominantly cold throughout the year. Then we have major chunk of the building of the country which are under composite. Composite climate like North India, UP, parts of Madhya Pradesh, parts of Rajasthan, Haryana, Punjab, Bihar, Bengal, Jharkhand, etc. These are the areas which kind of experience all different climates during different seasons. So during December, January, February, they face extreme winter. During peak summer months of May, June, July, they experience extreme heat or extreme summer, where the temperature can go as high as 45 degrees Celsius. During monsoon, they experience extreme humid weather. And there are also sailing period or moderate period when the outside is very pleasant, especially during October, November months or March month. So since these areas experience all kind of climates throughout the year, all kind of weather conditions, they are named as composite, and the buildings in this climate zone have to address to all these requirements of the different seasons. We also have hot and dry climate. Hot and dry is limited to especially the desert-like areas of the country like Rajasthan, parts of Maharashtra and Gujarat, where the daytime temperature can go very high, the nighttime temperature goes relatively lower. So there is a high diurnal range, which means difference between daytime temperature and nighttime temperature. Winters are practically non-existent in these climates. Throughout the year, it remains hot. And the relative humidity remains throughout the year very less or on the lower side. That's why they have been named as hot and dry. All along the coastal line of India, we have warm and humid climate. Thanks to the sea breeze, the temperature here is relatively not that warm. During the day, the peak temperature can go generally maximum up to 35-36 degrees Celsius. The nighttime temperatures are also not very low. They are very close to daytime temperature, generally 3 to 4 degrees lower than the daytime. Humidity is very high thanks to the moisture from the sea. These are the areas where people prefer a lot of good ventilation, because if with a provision of good ventilation, you can achieve thermal comfort. There are limited areas in the country which experience temperate climate. These are the cities like Mysore, cities like Bangalore, where throughout the year the outside conditions are very pleasant. They are never too cold, never too hot, never too warm, or even humid. So the conditions outside are very favorable. So the buildings need not to be designed to cut down too much heat or too much ventilation there. So the requirements for all these 5 different climates of India are different. Like I said, when Kerala state adopted ECBC and renamed it as Kerala State ECBC, they only published the requirements of warm and humid climate in the book, or in the Kerala State ECBC book, so that because the entire Kerala state is predominantly a warm and humid climate, and the state need not to look at the requirements of a dry or composite or temperate or cold. I will take you through some examples of traditional buildings in Kerala. We have seen these are quite traditional or even new, but designed in a. I will take you through some examples of traditional buildings in Kerala. We have seen these are quite traditional or even new, but designed in a traditional manner buildings, where the salient features used to be extensive wall shading and window shading. There used to be bands of corridors, not corridors, but verandas all around the house, so that all the windows and walls are well shaded. The verandas used to be a very lively spaces. People used to hang around a lot in the verandas because it used to be very airy. The walls used to be very porous with lots of openings, lots of windows, so that more and more ventilation can be allowed within the building. As in warm and humid climate, the temperatures are not too extreme. However, with the right amount of ventilation, with adequate ventilation, people inside the building will still feel relatively comfortable, thermally comfortable. So these were quite the salient features. Having traditional internal courtyard was another basic element in these buildings, be it commercial, be it residential, be it institutional. The corridors, these courtyards really help in bringing diffuse daylight in the house in the center. They also helped in better ventilation. They also helped in purging night heat or creating stack effect to keep the lower story cool. They also helped in making the internal space lively as well as comfortable from all perspectives. If we look at some of the government-made buildings like Kerala Legislative Assembly, you would notice that even these buildings, even though modern, still have a lot of elements from the traditional architecture of Kerala. For example, the walls are very well shaded. You can see a lot of vertical fence. You can see horizontal shade. The windows are very limited. The window there is ribbon windows. The window to wall ratio is limited. We do not have a glass facade here, although most of the windows are made operable or openable so that they can allow natural ventilation. Orientation was given due importance, and a lot of local design elements of the column brackets and all were integrated. So even these buildings used to give you a very clear idea that the building is designed for a warm and humid climate, with design elements taken and inspired from Kerala. However, if you look at some of the modern buildings that are coming up in Kerala, we see buildings which are completely glass facades, 100% glass. We see buildings which are completely sealed, so no scope of natural ventilation. relying mostly on air conditioning. Exterior shades are practically, invisible or insignificant. With so much of glass, it leads to a lot of heat gain within the building. The building acts as a glass box, as a greenhouse, and traps all the heat, increasing the air conditioning load and leading to higher energy consumption. So this is exactly what ECBC tries to reevaluate as a design option and give you guideline not to reach this level of design where the building is not at all responding to the climate, the building is not at all gemming well with the local architecture, or the building is not responding to the thermal comfort needs of the building, of the occupants. It relies highly on high energy intensive equipments and resulting in significant energy consumption increase in the state of things. So this is exactly what we have to change. Before moving further, I think to building physics, which is applicable and important to understand ECBC. Do we have any questions from my audience? So when we talk about ECBC and specifically envelope, like I discussed, the first chapter of ECBC, first major chapter of ECBC is building envelope. We need to understand building physics. So heat travels around through our building and what needs to be addressed there. So we first need to understand what is building skin or building envelope. It's basically the surface that separates external environment from the interior or the occupied space. So in this image, that blue line that you see is the skin of the, basically differentiates from outside to inside, from exterior environment to the interior environment. It includes roof, walls, floors, windows, doors, etc. It also includes windows, doors, skylights, etc. So this skin that you see in the blue line as a concept section has to meet the requirements of ECBC. And for that, we need to understand how heat travels in a building or through a building envelope. There are three modes of heat transfer, as we all know. We all have studied this in school. The three modes are radiation, conduction, and convection. Radiation is the method of heat travel where if there is a substance or any object at a higher temperature, and if there is an object at a lower temperature, then the heat can travel from higher temperature to lower temperature without having any medium in between them. So it means that to allow heat to travel, we do not need air or water or any other medium in between. The heat will travel by radiation. A classic example of this is how heat travels from sun to earth. Sun primarily being a hot object and earth being a low temperature object. The heat from the sun travels to earth. Even though there is absolute cavity or absence of any air or between earth and sun, the heat still reaches to us. Another example is when we have bonfire. We are sitting around the bonfire. In the bonfire, when the wooden logs are burned, the heat basically travels from that flame or from the burning part and it reaches our body through radiation. The second mode of heat transfer is conduction. Conduction is where the heat travels from high temperature to low temperature. through a medium. This medium can be
approved compliance tools.
This medium can be metals. These mediums can be any solid
mentioned.
or
EMS also
any contact. The heat travels because of continuous connection between molecules, where the high temperature molecules basically allow the heat to travel through one another from high temperature to low temperature. A classic example of this is when we heat up a pan on stoves or gas when we are cooking. If we have a handle which does not have any insulation, if it's a metal container and the handle is of the metal as well, then after some time, when the the utensil or the pot heats up, the handle will also heat up, unless there is a insulation between the handle and the pot, or the handle has any insulation. So you will feel that heat. So that is heat transferred through conduction, where although the heat is subjected to the bottom of the pot, but it still reaches to the handle through conduction. The third mode of heat travel is convection. Convection is a third mode of heat travel, where the heat travels due to difference in density of materials. For example, when we heat up anything, when we have a radiator in a room, or when we heat up anything, the air around that material will get heated up and will rise. So the heat is picked up by heat, and the density of the air gets low and it rises. Whereas the density of the cold air, it being higher, settles down, and hence the hot air rises and the cold air settles at the bottom. This leads to a movement of current, or the convection current, or we call air current, where the hot air will move to the top, will get cooled down, will settle, and then again come in contact with the hot object and will lead to movement of air. The movement of air also leads to movement of heat along with the air. And that is what we call convective current, convection, heat transfer through convection. Another example of heat travel through convection is in a hot water. If we are heating water in a bucket or something, and if we have the source of heat at the bottom, you will notice that the bubbles come up. That's because the hot water at the bottom gets heated up first and it moves up. As the hot water will move up because of lower density, and the cold water will settle down due to low density. So density is the major cause of movement of material there, which can be either air or water or any other gas or liquids. In a building, all these three modes of heat transfer are important, because all these three modes lead to heat gain or loss from the building. So to understand on a building section, conduction is responsible for heat gain from outside air to the inside through walls and roof and floors. The hot outside air, if the building is air conditioned at, let's say, 24 degrees Celsius inside, and outside is 35 degrees in a warm and humid climate, then the outside is at 35, inside it is at 24. So there is 11 degree temperature difference, 11 degrees Celsius. Hence heat will travel from outside to inside, and the material in between, which is the walls and the roof, will allow that heat to travel. Hence it is important that when we design our walls and roof, we design them with insulation, so that that amount of heat travel to the inside is reduced or limited or restricted by using thermal insulation materials or building construction materials, which can allow to reduce that heat gain through conduction. The measure or the term used for expressing this heat gain from walls and roof is U value or R value. The U value should be as low as possible in walls and roof, and the reciprocal of U value is R value, which means R value is resistance value, thermal resistance value. The more is the thermal resistance value, the lesser will be the heat gain within the building. So the roof and wall should be designed with a lower U value or a higher R value. by adding insulation materials and insulating construction surfaces to the walls and roof. Looking at the convection, we all know that buildings need fresh air, buildings need ventilation. When we are designing building for ventilation, the air outside, since it is hot, it will come in and will heat up the indoor environment. Even if we are doing mechanical ventilation with air conditioning, the air conditioning also requires that the fresh air is applied to maintain indoor air quality. Therefore, the hot outside air that we are bringing in needs to be treated so in order to reduce the heat gain. At the same time, when we are bringing in outside air, we are also exhausting the cold air or the conditioned air, which is poor air quality. So that poor quality air, which is yet conditioned, when if thrown out, should be dealt in order to retrieve its cooled character. So this can be done by different air conditioning measures, different equipments like recovery wheels, etc. There is another component of convection heat gain into a building, which is called infiltration. Infiltration is when we have building openings or cracks or gaps in the between different materials in the envelope,
Section
like gaps. The third mode, which is radiation, is we have heat gain through radiation in buildings from transparent and translucent building openings like windows, skylights, etc. The sun with its direct light will lead to significant heat gain. There is also indirect heat gain, radiation heat gain, which is from the different paved or construction materials around your building, which absorbs solar heat and re-radiate through long wave radiation, short wave radiation inside the building, infrared radiations. So those radiations, be it directly from the sun or indirectly from the paved surfaces around the building, should also be can also be prevented by having good quality solar shades or building shades and designing the exterior of the surroundings of the building with more greenery so that those indirect radiations can be prevented.
In our uploaded document in the website, ebook 2000.
When we talk about natural ventilation, we all know about single-sided ventilation, where a room has only a single-side window. So if a building is designed not to be air-conditioned, but with natural ventilation, then there are certain guidelines set by National Building Code 2016. The National Building Code 2016 should be clearly referred for compliance, even for ECBC, for natural ventilation. Where all we can have single-sided ventilation or cross ventilation. We all know cross ventilation is better than single-sided ventilation, as it allows more area of the building to be cross ventilated, to be properly ventilated, and stack ventilation, where we allow cool air to come through the bottom and let the hot air rise from the top. That allows even better mode of ventilation. It leads to even higher rate of ventilation. So if the building is intended to be naturally ventilated, the guidelines as given in NBC 2016 must be followed. Infiltration I've already spoken about. As you can see from the image, the joints between the walls and the ceiling, cracks between wall and the window frames, those are the openings which lead to infiltration or exfiltration, where the untreated, unconditioned outside air comes inside the building due to either temperature difference or through wind pressures, and must be dealt with. The building also has openings. We discussed about heat gain through radiation. The heat gain through radiation should be minimized by The heat gain through radiation should be minimized by having proper exterior window shades. These shades, along with the windows, are termed as fenestrations. The building can have any kind of exterior shade as long as it is, effective. So the project team should design effective window shades which allow the solar radiations to be minimized, yet allow daylight to come inside the building as natural light and prevent heat gain inside the building. There can be multiple ways of designing fenestrations. You can have horizontal shades, traditional horizontal and vertical shades. You can have louvers, you can have second skin. A lot of people now design with jali skins and a second shading skin to the building, which not only give act as a good performance, but can be a major aesthetic element in the building design as well. The building needs to address its window to wall ratio. Window to wall ratio, WWR, is the term used to explain or refer to the amount of glazing we have in a building. So it is basically the amount of glass area divided on the exterior walls divided by the total exterior wall area. If we divide the total glass area on the exterior wall by the total wall area on the exterior, it gives us window to wall ratio. If the window to wall ratio are higher, it means there is more heat gain, more daylight, more solar heat gain from the exterior. However, if we have less amount of window to wall ratio, that would lead to lesser daylight, lesser heat gain. Hence, there needs to be a fine balance between daylight and heat gain. Therefore, the ECBC gives you a limit on how much window to wall ratio a building should have, and recommends to ensure that the windows area is not more than 40% of our total exterior walls. 40% window to wall ratio has come up through many project studies, many case studies, many simulation analysis, where it is found that beyond 40% window to wall ratio, if we have more glass, then there would be no significant benefit on the daylight, although rather it would be unnecessary daylight which leads to glare, which prevents proper working in the building, which prevents people working comfortably inside, and lead to a lot of solar heat gain as well. Hence, the window to wall ratio should be balanced. While designing the buildings, it should be our first key to balance between daylight and solar heat gain in the building. Having a building which has high window area, even if you have very good quality glass, will not give you a good performance building. So the window to wall ratio should be very well optimized for all projects.
In section 5.2.2.1, in minimum space conditioning equipment efficiencies under chiller.
As for daylight, we know daylight is basically the purposeful light brought inside the building so that our dependency on artificial light is minimized. However, when we are allowing sunlight to come inside through windows, there is an element called glass.
Chiller shall
And the
meet
glass
our
properties are very important
requirement
for
as
daylight in the building.
If
the glass has
minimum
visual light transmittance property to be very low, we call it VLT, which is visual light transmittance. If the visual light transmittance value of the glass is low, that means the glass is darker in color and will allow lesser light to come in.
For chillers is removed.
Very low quality daylight, very low VLT would mean practically poor quality daylight. However, high VLT would mean more daylight in the building as well.
Check metering
so
and
the daylight has to be really optimized in the building in order to allow comfortable working of occupants.
kVA shall
We do
be
not want too much glare inside the
meeting
building.
record demand,
Hence,
energy and total
the VLT should also be optimized.
Only basis was
However,
not mentioned, but it is
in order
included.
to optimize the VLT, we should not make it too less also, because lesser VLT or visual light transmittance would mean lesser quality daylight entering the building, and that will lead to our increased dependency on artificial lighting. That means Even after having windows, we will resort to options like using artificial lighting during the daytime and will lead to increased energy consumption in the building. We should always design our building such that the windows are very well shaded, so that there is only diffuse daylight within the building, not direct daylight. The diffuse daylight can be really a boon for the building, because it prevents any heat gain while still allowing your natural light in the building and reducing your dependency on artificial light. As for the solar heat gain, like I said, solar shades are very important, but we need to understand the building physics behind how the radiation or the solar rays react with our windows. As we get the solar rays falling on our windows, the glass within the window will reflect some amount of that light to the outside and allowing the remaining to go inside. There's a small fraction of the heat coming from the sun in terms of infrared rays, which will also be absorbed by the glass and will eventually be emitted outside as well as inside. So the total component of heat, or solar heat or infrared rays or total heat which has come from outside to inside is total amount is referred to as solar heat gain. It is generally calculated through a term called solar heat gain coefficient in glass and in windows. It is the total solar heat transmitted inside directly or re-radiated to the inside. Typically, a higher SHGC or higher solar heat gain coefficient value will mean that a high amount of solar radiation from outside is reaching the inside of the building. While if the SHGC or solar heat gain coefficient is low, it means that the solar heat gain is minimized in the building to that extent. To reduce, we all know now that we would like the project to have glasses with high visual light transmittance but low solar heat gain coefficient. The solar heat gain coefficient can not only be reduced by choosing glasses which have low E coatings or which are double glass, or glasses which have metallic tint to it or metallic coatings as a tint to reduce that heat gain and increase the amount of reflected outside radiation. But we can also design our windows where we can have exterior shades, because if the major component of solar radiation is cut down by exterior shade, then the glass need not to be designed as a double glass or as a glass which has very low SHGC quality, because the solar shades have done the major part of reducing the solar heat gain. Kindly please note that having a glass which has generally very low SHGC would also mean that the visual light transmittance will be reduced. So there is a fine balance between these two. So the project team would always like the solar heat gain to be as less as possible. At the same time, VLT to be optimized, or the visual light transmittance value of the glass to be optimized, which can very easily be achieved by effective solar shades and by having glass which is DGU and relatively lighter in color, which optimizes both SHGC, solar heat gain to the building, as well as the daylight inside the building. For a warm and humid climate, it is very important that a low SHGC value is more important than the low U value in the glass. The U value of the glass would mean the low conductance heat gain. Therefore, shaded windows or low SHGC glass will help you in reducing more heat gain than double glazing. What I mean here is that sometimes, especially in the warm and humid climate, shaded windows will work better than shaded windows with single glass can work much better than doubly glazed windows without any shade. For designing window shades, we all know about vertical shades and horizontal shades. If there is windows above the horizontal shades, then the horizontal shades can also act as light shelves, which help in better daylight penetration in the building, which helps in better good quality daylight within the building. So we should design our buildings which are having windows which are properly shaded with glass with relatively high VLT, so that the heat gain is minimal while the quality daylight is there and our dependency on artificial light and air conditioning is minimal. So we'll now discuss ECBC compliance requirements. What are the methods of ECBC compliance? So, like I said, the ECBC is divided into 5 major chapters or major sections, being envelope, HVAC, lighting, electrical power, solar, hot water, and pumping. You may note that all these 5 sections have certain mandatory requirements. These mandatory requirements are absolutely necessary for all projects to meet. None of these requirements can be avoided for compliance in any project. In addition to these mandatory requirements in these 5 sections, there are also certain prescriptive requirements. Prescriptive requirements are available in envelope section, in lighting section, and HVAC section. These 3 sections, the top 3 sections, have prescriptive requirements. The prescriptive requirements are basically the requirements or guidelines which are given to the project team in the code, which they can follow to meet energy performance in a building. For example, in envelope, we have prescriptive requirements on what U value or thermal conductance value has to be achieved for walls, for roof, for glass, for skylights. The prescriptive requirements also deals with the SHGC requirement for glass and the VLT requirement for the glass. Whereas the mandatory requirement in envelope are addressing the air tightness factor, the method by which the U value should be calculated, the method for calculating solar heat gain coefficient in the building, etc. So the methodologies of the calculation and minimum air tightness are the mandatory requirements of envelope section, while what U value should be achieved and what SHGC value and WWR, window to wall ratio, be achieved in the envelope are the prescriptive requirements. These are direct guidelines given to you which can be used by the project team to meet compliance. However, if within the envelope section, if any prescriptive requirement is found to be difficult to be achieved by the project team, only the prescriptive requirement, if any of the prescriptive requirement is found to be difficult to achieve in the project for any XYZ reason, then the code also gives you an alternate compliance path, and that alternate compliance path is trade-off option for envelope. So the trade-off option basically deals with if any one particular prescriptive requirement is compromised, then 1 or 2 prescriptive requirements are compromised in the project to a certain degree, then the other elements of the design have to compensate for that limitation or that drawback, such that the overall heat gain inside the building is still same as you would have achieved with the prescriptive requirement. So that is a trade-off between different elements of prescriptive requirement as an alternate compliance path. For HVAC, we have prescriptive requirements and mandatory requirements. The mandatory requirements are related to what should be the efficiencies of the air conditioning systems and equipment installed in the project, what should be the minimum insulation values that has to be achieved for chilled water piping or refrigerant piping or duct insulation, etc. How the natural ventilation should be achieved and the requirements for natural ventilation in a naturally ventilated building, which are as per MVC. So those are the mandatory requirements. Whereas the prescriptive requirements are related to what kind of fan we can use in the cooling towers, or more efficiency equipments to be used in HVAC system for the air conditioning or thermal comfort in the project. However, if any prescriptive requirement is found to be difficult to be met in the project, then the project team can opt for a whole building performance approach. The whole building performance approach allows that a trade-off not only within the HVAC section, but also between different sections of ECBC. For example, if a project is not able to meet certain requirement of envelope either by prescriptive, neither by prescriptive nor by the trade-off method, then the project team can use whole building performance method such that the HVAC section, the air conditioning or the lighting, compensates for that additional energy consumption due to envelope and ensure that there is no more energy consumption than the baseline case. I'll explain you the whole building performance method more in detail, but the key element to understand here is that there are certain mandatory requirements in the project in ECBC for all these sections. Then there are prescriptive requirements in envelope, HVAC, and lighting. And if these prescriptive requirements are not met, then you also have an alternate compliance path by using whole building performance approach, which gives you a trade-off between different sections of the ECBC as well. Within envelope, there is a third alternate compliance part, which is trade-off method within envelope only, which can also be used by the project team to show compliance. For the envelope, like I said, there is a mandatory requirement, there is a prescriptive requirement, and an alternate to prescriptive requirement is the trade-off calculation option. And as an ultimate trade-off, we have whole building performance approach. The whole building performance approach is basically a process where we create a computer simulation model, energy simulation model for the building, and we estimate what would be the energy consumption for the project. To create that energy model, the project team utilizes the actual building drawings and design, because the model will mimic its actual building geometry, its actual window to wall area, ratios, orientation of the building, inputs. There are several inputs which are used in whole building performance approach, like building schedules, when will be the building utilized, when will it be occupied, when the different equipments, air conditioning systems, lighting, etc. will be switched on or will be utilized in the building. What kind of different construction materials will be using in the building will be modeled for the energy model for envelope section. You will also model efficiencies of different air conditioning systems. Different kind of air conditioning systems also can be modeled in the whole building performance approach, whether it's a conventional window AC, split ACs, or if it's a central chiller plant with conventional air handling units for air cooling, or whether we have radiant cooling system, which is quite innovative method of air conditioning, or underfloor air distribution system, or air stratification system, or natural ventilation, mechanical ventilation, or even utilizing geothermal energy in air conditioning systems. So all these different kind of air conditioning systems can also be modeled well in whole building performance approach or the energy model. The lighting systems can also be modeled in the whole building energy simulation approach by considering the lighting power densities that we achieve in the project and the lighting controls we have in the project, daylight sensors, integration of daylight sensors or occupancy sensors. So all these different controls and lighting systems can be modeled very well in energy model, along with the schedule of when they are utilized, when they are switched on, when they are switched off, exterior lighting, even other equipments like computers, STP, lifts, plumbing panels and motors, all these exterior lighting, etc. The energy model comprises of all these different elements and then estimates what will be the total annual energy consumption, how much energy the building will consume every hour of the year, which are 8760 hours in a year. So for every, it will calculate what will be the energy consumption for every hour of the year, every week, every month, and overall for the total year. What will be the total annual energy consumption? Now, that model can be tweaked with the requirements of ECBC, the prescriptive requirements of ECBC, and energy consumption would be calculated for the same, and it can be compared with the proposed design to see whether the proposed design is meeting the requirement or not. So we basically create two models. One is called a proposed design and second is called a standard design. Standard design is basically a base design which is based on the prescriptive requirements of ECBC, and proposed design is the actual design with actual building materials, actual HVAC design, actual lighting design in the project, etc. We compare the two energy models and see what will be the energy consumption in both of these. And upon comparison, the proposed design should be either as energy efficient as the standard design or should be more energy efficient than the standard design, to understand that to make it compliant to the for ECBC. If the proposed design's energy consumption is less than the standard design, then it will be acceptable as whole building performance simulation approach. Whereas if the proposed design's energy consumption is more than the standard design, then the project will need to tweak its proposed design in terms of its envelope measures, or in terms of its air conditioning HVAC measures, or in terms of its lighting measures, to come up with a model which has lower energy consumption than standard design. When we go with the whole building performance approach, this gives you a lot of flexibility, because the project team need not to meet all the prescriptive requirements of the project. There can be a trade-off between different prescriptive requirements, not within a section, but also between different sections of ECBC, where if the envelope, building envelope is not so efficient, then the HVAC can be made more efficient, or the artificial lighting system can be made more efficient in the project. So this is one of the alternate approaches which are available in ECBC. For creating energy models, there are different energy modeling tools available in the market. Some of the recommended and some of the authorized softwares or approved softwares by ECBC are Equest, Energy Plus, Design Builder, IESVE. These are 4 software which are approved by ECBC to be used for energy modeling. I would you may notice that Equest is a software which is free to use. It is freely available in on the internet. You can download it and you can learn it, and you can use it for the projects. Equest is a very popular software. Energy Plus is also another free software available and developed by Department of Energy. Both these softwares, Equest and Energy Plus, are developed by Department of Energy, USA. However, Equest has its own user interface. Energy Plus does not have its own user interface, and it's little difficult to use. However, if you integrate, or if there are additional softwares available in the market which you can use along with Energy Plus to make your modeling easier. For example, SketchUp along with some plugins for with Studio, Open Studio can be used for Energy Plus modeling. Design Builder is another software which primarily uses Energy Plus as a simulation engine, whereas the modeling interface can be used from Design Builder. IESBE is another software which is very popular for energy modeling, for daylight modeling, etc. in the project. All these softwares can be used for energy modeling. These softwares, these are different softwares. They can have different interfaces and different way of working. However, you may note that all these softwares will require same amount of data or same amount of input for your energy model, which means you have to tell the software what is the actual geometry of the building, what is the orientation of your building, what different materials are being used for the building envelope, what different strategies of air conditioning are used in the building, what are the schedules for occupancy, lighting, air conditioning, etc. What is the level of infiltration in the building, so on and so forth. So all these softwares require same amount of data for correct energy modeling. ECBC also gives you a lot of help in terms of how what should be the standard practice for making your proposed design and for your standard design. What all parameters one has to consider for schedules, what all assumptions you need to make. It gives you a lot of guidelines. ECBC gives you a lot of guidelines on those terms as well. HVAC, as we know, is the heating, ventilation, air conditioning. It is the next section of ECBC, which is required to be met the mandatory requirements as well as the prescriptive or whole building simulation approach has to be used for compliance for HVAC. The project team should always use the right approach, which we call as design optimization approach. The approach always considers that firstly, the project team should choose a right building form and correct building orientation, because that will have the maximum passive measure strategies and will have the maximum energy saving potential in the project without spending anything on the building. The next should be the building envelope. Building envelope should be optimized to prevent heat gain or heat loss, to allow right amount of ventilation, to prevent infiltration, and to allow good quality daylight in interiors and minimize heat gain from the exterior. The next stage for the project team should be to select right thermal comfort approach. What indoor set points and indoor conditions the project team wants to achieve in order to provide thermal comfort for the occupants. Because we all know if we keep our air conditioners at a higher degree, for example, 26 to 27, that would mean that there would be significant energy savings as compared to the same building, same air conditioner being run at 22 degrees or 18 degrees Celsius during summer, during hot period. So thermal comfort conditions, if chosen appropriately for the building or designed appropriately, can also contribute to significant amount of energy efficiency and energy conservation. The next strategy should be to select right kind of HVAC system in the project. Should you go with unitary air systems like window ACs, split ACs, or should you go with central chilling plants like VRF or VRV, or should you have central cooling plants like chiller plants, cooling towers, condenser water pumps, chilled water pumps, air handling units, etc. Or should you go with a more innovative systems like radiant cooling or underfloor air distribution system? Ultimately, when the project is built, when the systems are installed, the project should also do building commissioning. Building commissioning means checking all these factors properly throughout the building design, construction, implementation, and installation process, and checking whether all these systems which are installed in the building are working properly to provide thermal comfort, are designed properly to address heat gain from the building envelope, and meet the right comfort for the occupants and achieve their energy efficiency as well. Under service hot water and pumping, we all know the hot water is required in buildings for domestic requirements like cooking, cleaning, bathing, space heating. We also need hot water in commercial buildings for cooking, laundry, bathing. In hospitals, it is also used for cleaning, disinfection, etc. And there can be industrial use as well. Since industrial projects are exempted from ECBC, we'll mainly discuss the domestic and commercial requirements. To generate hot water in building, we either have several type of water heating systems. The heating systems can be conventional systems like electricity based or natural gas or LPG based, or oil based or solid fuel based water heaters. There are also alternate energy source types for hot water. Very popular ones are solar hot water systems, where we use solar energy for active or passive heating of water. There can be heat pumps also. Heat pump basically utilize the refrigeration cycle for heating water more efficiently than the conventional heating systems. We can also use hot water recycling to recover heat and to heat up water. We can also use geothermal heating, which is again a renewable source of heating. So all these alternate appliance, alternate energy sources are applicable in ECBC and can be used for compliance method. The solar hot water systems are also divided based on their hot water storage, whether it's a storage-based system or an instantaneous-based system. The storage-based system obviously means that there is a hot water storage in the building, which means that there would be storage losses. Hence, the storage unit or the storage has to meet its insulation values or the insulation requirements so that the storage losses are minimized. At the same time, the instantaneous systems are where the water is heated and instantly supplied to the taps to the water requirement areas, the water requirement zones. In these systems, the distribution of hot water should be designed so that the transmission losses or the pipe losses are minimum. So the hot water section of ECBC basically deals with all these requirements. What kind of heating system should we have in the project? Whether the heating system is conventional or is a non-conventional system. What are the efficiencies of these systems? What are the efficiencies of the storage units and the transmission systems in the project? Further, on the electrical side, the electrical requirement are only mandatory in nature. In ECBC, there are no prescriptive requirements. The mandatory requirements basically deals with the scope of electrical system starts from the transformer and the electrical systems within the project or within the facility. Beyond the transformer, the distribution network of the central grid, etc., are not part of ECBC compliance for a project, as they are not in the purview of the project team. Hence, transformer and the services which come under the electrical services which come under the facility or the project need to meet the ECBC requirements. Starting with the transformers are used to change the voltage from HT to LT, from high tension to low tension, from high voltage to low voltage in a project. Therefore, the transformers lead to a lot of inefficiency. However, these losses, energy losses through the transformer, should be minimized by using rated transformers in the project. These transformers have to be rated both at full load as well as part load, because the building do not always run at its full load. Further, as the energy or electricity is supplied to the facility, the different systems which are installed in the project, starting from equipments like distribution network, how the energy is being distributed within the project, the cable sizes, the cable sizing, the transmission losses, etc., should be properly calculated and addressed to meet the mandatory requirement of ECBC. The energy supplied to various systems like motors and pumps and these motors and pumps should also be energy efficient and should meet the requirement of ECBC for its minimum efficiencies. Further, all electrical appliances, the major energy consuming appliances like lifts, like air conditioning systems, like STPs, etc., should be properly metered. So it should be properly sub-metered. These sub-metering should be done adequately as per the guidelines of ECBC to measure different components or different parameters of energy. There should also be a proper provision for integrating renewable energy in the project, which is a requirement of ECBC. The renewable energy system, there should be proper provision for installing solar energy systems or other modes of renewable energy like wind energy or geothermal energy, etc., in the project. All these requirements are mandatory in nature in the project and in ECBC.
As we come to the end of today's program, I invite Mr. Thompson Sebastian, Energy Technologist, Energy Management Center, Kerala, for the vote of thanks.
Good afternoon, everyone. On behalf of the Energy Management Center, Kerala, I would like to express my gratitude to all esteemed delegates of the webinar for their presence and contribution to make this awareness program a great success. I extend my gratitude to our keynote speaker, Dr. R. Kumar, Director, Energy Management Center, Kerala, for his inspiring and encouraging words on this day. A special thanks to Mr. Akshay Gupta, ECBC Master Trainer, for this enlightening session on ECBC. I extend my gratitude to Mr. Dinesh Kumar AN, Joint Director, EMC Kerala, for his welcome address and providing support to organize this webinar. I must thank the Energy Efficient Building Cell team for working hard for the past few days to make this webinar successful. And tomorrow there will be. Thank you, everyone, once again for making this program a success. Thank you.